In this paper, we present a new approach for visual explanation of classifiers. What do we mean by explaining a classifier? Let's see an example. Say we want to explain a dog versus cat classifier, and we want to understand why this specific image was classified as a cat. Previous approaches include attention maps, which highlight important regions in the image that affected the classification, such as the eye area in this case. But what is it about the eyes that made the classifier decide it's a cat? Is it their shape, color, size? Attention maps cannot provide such information, and they are useful only for spatially localized attributes. Another approach provides explanation via counterfactual examples. These are statements of the form, if input x were changed to x prime, then the classifier output would change from y to y prime. Prior work in this category include methods like GANalize, which smoothly transform the image between one class to the other. However, these methods tend to change all attributes at once, thus making it difficult to isolate fine-grained attributes. In contrast, our approach automatically discovers disentangled attributes which affect the classifier. For each discovered attribute, we generate a counterfactual example. For instance, for a dog versus cat classifier, we provide the top discovered attributes. Moving each knob manipulates only this specific attribute in the image. For example, the first discovered attribute is folded ears. Another discovered attribute is open mouth. And another one is the pupil size. So how does it work? Given a classifier and an input image, we wish to find and visualize the individual attributes that affect its classification. For that, we use the StyleGAN v2 architecture, which contains a disentangled latent space called StyleSpace. We train the generator to satisfy the classifier, thus encouraging the StyleSpace to accommodate classifier-specific attributes. This is obtained by training the StyleGAN generator with two additional components. The first is an encoder, trained together with the GAN, with a reconstruction loss, thus forcing the generated output image to be the same as the input. This allows to explain the classifier's decision on any given input image, but visual similarity is not enough. The GAN should also preserve the classification probability of the image. To ensure this, we add a classification loss to the StyleGAN training. This guarantees that subtle visual details important for the classifier, such as medical pathologies, will be included in the generated image. We call our end-to-end system StyleX. Once trained, we search the style space for attributes which significantly affect the classifier. To do so, we manipulate each style space coordinate and measure its effect on the classification probability. For example, if we alter this style coordinate, we obtain the following difference in the generated image. We then measure the difference in classification probability between those two images. We repeat this for each attribute. Here is another one. And another one. We seek the top attributes that maximize the classification probability difference for this image. This provides the top k image-specific attributes. By repeating this process for a large number of images per class, we can further discover the top k class-specific attributes, which teaches us what the classifier learned about this specific class. Let's see a few such examples. We already saw an example of image-specific explanation on the cat image. Let's now see some examples of class-specific explanations. For a perceived gender classifier, here are the top 4 detected class-specific attributes exemplified on multiple images that best demonstrate them. The first attribute was a beard. The second was a mustache. A lipstick attribute. Eyebrow thickness, etc. Our approach works on many domains and was used to explain many different classifiers, including the perceived gender classifier, which you have already seen, a perceived age classifier, a retinal image classifier which detects diseases based on very subtle image details, a birds classifier with 200 different classes, a leaf disease classifier, an animal classifier, and more. Our StyleX method can be used not only for explaining what a classifier has learned, but also detect unknown features in medical images which can help diagnosis, and detect biases in classifiers and datasets. For more details and many more visual results, please see our paper and project website.